good. I think that the extra half hour helped. So let's start now this morning session with Eduardo Miranda, who's going to talk about Mott domain wall matter.
Thank you. Thank you very much. First of all, thanks for the organizers for giving me the opportunity to speak here. I'm going to talk about Mott domain walls, which is something we saw yesterday in Andres' talk. The work was mainly done by these two former students, Tu Hung Lee and Martha Villagran, and in collaboration with this colorful character, which many of you may know, my good old friend, Vlad Dobrosavljevic. And okay, so let's start. So, Mott transition. There are basically three, or perhaps two scenarios that we have for this very important problem in condensed matter physics, which has to do with the question of whether the Mott transition is a first-order transition or a second-order quantum phase transition, a zero-temperature transition. So the first scenario is this one here. You have a quantum phase transition between a Fermi liquid and a spin liquid, perhaps, and it's a second-order transition. Oh, that's what I said. There are very interesting questions about the nature of this quantum critical point, and of course of the spin liquid on the other side. There is some evidence that, recent evidence that some of these Moiré superlattices have an actual two-dimensional. This is a scenario that's especially important in two dimensions, where you don't expect long-range magnetic order at finite temperatures. So these compounds, you have good evidence for a second-order transition at zero temperature. But then there's also the more, I would say, the more usual scenario where there is a first-order phase transition line that goes up in temperature and ends at a quantum, not at a quantum critical, but at a critical point, a critical endpoint, which is here. And okay, so I'll show you later that this is the most common situation. And of course, at low temperatures, you may have other instabilities like antiferromagnetism, superconductivity, depending on what kind of interactions you have in your system at low temperatures. But what we like to call the Mott transition is this first-order line that ends at this second-order point at finite temperature. And as you cross this transition, you have the metal insulator transition. Let's see. Okay. So this picture of a first-order line ending at a critical point is very reminiscent of the liquid-gas transition that we know from, I guess, undergraduate studies. So the line that separates the liquid from the gas ends at this critical point, and you can actually go continuously from the gas to the liquid without any abrupt changes in your system. So this is very similar to this Mott transition at finite temperatures, where you can go from an insulating-like behavior to a Fermi liquid-like behavior continuously if you go up above that critical point. So this is data on V2O3 doped with chromium. Some of these data you saw yesterday in Andres' talk. So I already said that. Okay, so this is more data on that system. If you look at the change in conductivity as you cross the first-order line, you see a jump in the conductivity. And as you study that jump, as you go up in temperature towards the critical point, that jump becomes very small and goes to zero. So it's very similar to the usual liquid-gas transition, where the gas density and liquid density are different, but they become almost the same as you go up towards the critical endpoint. Now, just like the liquid-gas transition, this transition here belongs to the so-called Ising universality class, the universality class of the Ising model. And actually what this very famous paper showed is that if you look at the critical behavior close to the critical endpoint you see that you actually have precisely the critical exponents of the Ising model, okay? And it's interesting because if you are not too close to the transition, the behavior is very mean field-like, but if you get very, very close to the critical point, then you recover the well-known, non-trivial critical exponents of the 3D Ising model. So the Ising model transition is described by a scalar order parameter, which in the case, for instance, of the liquid-gas transition is the density of the compound. And as I said, this is also analogous to this conductivity behavior here. Now, very old work done by some of my colleagues here showed that you can describe very well this transition within a theoretical approach that we heard about this week called dynamical mean field theory. I'm going to describe very briefly later on what this is. But it is able to get that kind of first-order line ending at a critical endpoint. My focus here revolves around inhomogeneities. So you can think about these as disorder-driven inhomogeneities, perhaps some other source intrinsic to the compound. But what you see, for instance, oops, I'm getting confused here. In this compound, VO2, which is a classic compound showing metal insulator transition, if you look at this infrared data from Basov's group, you see this kind of spatial fluctuations of metal and insulators. So the color scale here is showing that you have regions which behave like insulators, insulating-like behavior, and regions that behave like a metal. And you have this coexisting puddles of metals with coexisting puddles of insulating behavior. And this is a microscopic view of what's going on. So, as I said, you have domains of metals and domains of insulators. Conductivity, taken from this infrared spectroscopy, which is quite non-trivial, but that's what it, at the end of the day, that's what it means. So, so this is from Andres. Thank you, Andres, for this picture. This is sort of the same measurements on V2O3, which is the other classic Mott system that goes through a metal insulated transition. And you also see these domains. As you go through the transition, you see these domains of metals and metal and insulator. And you see here, this is hysteresis because this is a first order transition, so you expect hysteretic behavior, and you can go up from above the upper part of the hysteresis loop or the lower part, and you see the formation of these domain walls. Now, this can actually also be captured in an extension of the dynamical mean field theory, which I mentioned before, an extension that allows for the introduction of disorder. Okay, so the bare bones model for the metal insulator transitions, we can discuss whether this is enough for instance, V2O3, but this is like the hydrogen atom for the Mott transition, which is the Hubbard model. You have the kinetic energy term, the Coulomb repulsion, on-site Coulomb repulsion, and in this case of disordered systems, you put some kind of disorder potential, in this case, a local disorder potential, that with random energies that are distributed according to some distribution. Doesn't matter too much which kind of distribution. In this case, we can think of uniform distribution of energies per site. So the extension of the dynamical mean field theory that takes into account disorder is called, for historical reasons, statistical dynamical mean field theory. And now I'm going to tell you a little bit about what this theoretical description means. And basically what it does is to describe the effects of local electron-electron correlations. In other words, the on-site effect of electron-electron repulsion But in this case, because of disorder, this will be different from site to site. So in the picture, you can imagine your disordered system like this. You can sort of attach to each site self-energy, which takes into account the interactions. So if the interaction goes to 0, the self-energy goes to 0. And it is going to be different from site to site. Okay? Now, usually in a generic system, the self-energy will also depend, for instance, on two sites, in the disordered case, on site I and site J. So this description ignores those correlations and only focuses on local correlations on each site. Okay? So this is an approximation, but as I said, this captures the clean transition very well. Now, how do you calculate these things? Well, basically, you look at each of those sites as if it were a single site Anderson model, a single impurity model, that sees the other sites in a mean field way. So it sees the rest of the lattice as a bath of conduction electrons that can hop out of the bath into the impurity, out of the impurity into the bath. Okay? And you have to calculate one impurity, ideally one impurity site. Each, you have to solve a single impurity site for each site of your system. So it's a very demanding, actually, theoretical calculation. Now, some limits of this approach, if you take the limit of U going to 0, then the self-energy disappears, but the approach is basically exact in this sense. So, for instance, it has Anderson localization if you just ignore interactions. As I said, if you now turn off the disorder, you recover the usual dynamical mean field theory that gives you the first order line that I showed before. And of course, in this case, the self-energy is uniform, doesn't fluctuate from site to site. So as I said, in the general case, you have one single impurity problem for each site, and you have to do self-consistently the calculation for the whole lattice. It's a very demanding type of calculation because of disorder. So one of the effects of disorder is that we get the kinds of domains that we saw before, insulating domains and metallic domains that you can see here. So for instance, this is for large U. You have basically insulating behavior, which is the blue color, metallic behavior for a small u, and in between you have these coexisting domains of both behaviors induced by the frozen-in disorder of your system. So this is as a function of system size. As you grow the system, you see these domains appearing and so on. So as I said, statistical dynamical mean field theory is able to capture the domains that you saw experimentally in those plots. As you can see here, just like in the experiments, these domains can be very large, and the domain walls can also be very large. So if you fix the green color to be the domain wall between the blue insulator and the red metal, you see that in some cases, you have a very, very large domain walls between the two types of behavior. And I'm going to focus on the behavior on the domain walls in this talk, in the rest of this talk. So basically, the question I want to answer is this one. What is the physical nature? What is the physical state of the domain wall? Okay, we know the insulator, we know the metal. We want to explore the physics of the domain, what we call domain wall matter. So the first thing we did was to take a snapshot of this domain. And if you imagine that one dimension, here it's a two-dimensional calculation, but if you imagine that this dimension doesn't matter much, you can think that this is a straight domain wall, and everything that's interesting happens as you cross in the perpendicular direction from the metal to the insulator. So you can model this. You can do better. You can look at this actual thing, but of course, this is much more complicated. So you can simplify matters if you just take a one-dimensional model where you pin the system on the left to the metal, on the right to the insulator, and you study what happens as you go from one to the other. So this is the kind of thing that happens. This is the local density of states as you go from one to the other. You can see that well, this is actually rescaled and reshifted. But basically, the local density of states is expected to be 0 in the insulator, finite in the metal. And you have this nice continuous behavior as you go from one to the other. And as you approach the critical endpoint, so this is the first order line, the green line, ending at this critical point here. And as you approach the critical endpoint, as in any second order phase transition, the correlation length diverges. So you see actually this reflected in the size of the domain wall, which becomes very, very large as you approach TC. Actually, this is the inverse of the domain wall size. It goes to 0, which means that domain wall size goes to infinity at the critical endpoint at TC as you go along the green line. But it also goes to 0 at 0 temperature because within dynamical mean field theory, this endpoint at 0 temperature is also a critical point. I'm not going to have time to go into that behavior, but it's also a critical point, and there's also a divergence at 0 temperature. But this is not the focus of this talk, so I'm not going to talk too much about this divergence here. Okay, so we have this well-defined domain wall, and you can look, for instance, this is a very rough calculation where we did not do analytical continuation, so this is in Matsubara frequency axis. We just look, this is a technical point, at the first Matsubara frequency, and you wave your hands and you imagine that, okay, this is the 0 frequency behavior. And you can see that, for instance, in the metal, the scattering rate goes to 0 as you lower the temperature. In the insulator, it goes up. And as you might expect, at the center of the domain wall, so this is at the center of the domain wall, the scattering rate is sort of flat. So it's neither metallic nor insulating. So it's weird. Okay? So we wanted to look more closely at this behavior, but I want to resort to the Ising description of the transition at this point. So the Ising model also has domain walls, right? You can have, for instance, up magnetization here, down magnetization here, and between the two extremes, you have a domain wall. And the coarse-grained description of an Ising model is given by the so-called Landau functional, Landau mean field theory, basically, where you solve the equation for the order parameter, which I called phi here. This is the Landau functional. You minimize it, you get a differential equation for the order parameter. And you know that it should go to, let's say, +1 on one side and -1 on the other, and it should somehow interpolate continuously from one side to the other. Okay, so so this is the Landau potential, the usual 2 minima on up magnetization, down magnetization, and as you cross the domain wall, you go from one minimum to the other. So you have the order parameter doing this kind of smooth interpolation between one and the other. So you're going from one side to the other as you cross the domain wall. So the interesting and important point that I have to emphasize here is that the center of the domain wall corresponds to the maximum of the Landau functional. Okay? So when we solve the mean field theory, we are usually looking for the minima, which are either plus or -1 in this case. But the domain wall corresponds to the unstable solution of this problem, which is not what one usually looks for, okay? And that's the important thing for me today, okay? So just like in the Ising case, we can do a sort of a Landau functional description of this transition, and the domain wall will correspond to the unstable solution, just like in the Ising case. So you're going from the insulator to the metal, and at the center of the domain wall, you should be governed by the unstable solution of this Landau functional. Okay, so the dynamical mean field theory is a mean field theory, so it does have a description of this type that I'm showing here. So I'm going to briefly talk about what this description is. This has been done before. You can write down sort of a Landau functional for dynamical mean field theory, except that in dynamical mean field theory, the order parameter is not one number, one field, like we had before, but it's actually a function of frequency, which you can take to be the self-energy, as I showed before, or the local Green's function. It's the same thing. Not the same thing, but it's equivalent description. So you can write the Landau functional. It has this form. This is the free energy of the impurity problem for a given bath of electrons described by this local Green's function G. And if we minimize this functional, you get the dynamical mean field equations. Okay? So the first thing you can do a rough estimate of the unstable solution. You just write down the metallic solution, the insulating solution, and you sort of interpolate between the two with a parameter called L. So this is sort of a simple mixture of metal and insulator. Okay? And then you can, for instance, construct the Landau functional F basically by integrating from one endpoint, the metallic, say, to the other endpoint, the insulator. And you have precisely the kind of two minima you had before in the Ising functional case. But you also have to go through the unstable solution as you cross. Now, of course, you can use this as you can use the solution, the L that corresponds to this maximum here, as a first estimate of the unstable solution, and then you can use a more numerical approach to find the actual solution to the minimum of this, the unstable maximum, not the minimum, the unstable maximum of the functional that corresponds to the center of the domain wall. And there are conventional methods that allow you to find a maximum of the potential instead of a minimum. Okay, so this is the Breuden method. And we did this for a trajectory, a constant U trajectory as you lower the temperature. So let's see what happens to the domain wall as you do this. So the first thing you could do is take, you imagine that domain wall is very large. You have a metal over there, an insulator over there, and you have this huge domain wall. You can think of this domain wall as roughly a constant. Everything is almost uniform here. And you can calculate what the conductivity is for this large region of the domain wall. And dynamical mean field theory gives you the recipe for that. I'm not going to go into the details. And you can plot the conductivity and compare it to the so-called Mott-Regel limit, which corresponds to a scattering length, which is basically equal to one lattice parameter. So in a semi-classical description of scattering, the smallest mean free path that you could have in a solid is equal to the lattice parameter, because there's nothing happening at a shorter length scale in a solid. So this defines the Mott-Regel limit, and I'm going to write the conductivity rescaled by this limit. So this is the situation. This is the insulator. These are two methods for solving the single impurity problem, iterated perturbation theory and quantum Monte Carlo. In the insulator, you have this is the resistivity, the inverse of the conductivity, the resistivity going up in both methods. In the metal, it goes down, like a good metal. And as we saw before, the domain wall has a resistivity that goes up as you decrease the temperature. So the metal is a Fermi liquid. The insulator is an insulator. And the unstable solution is sort of weird. Okay? And I also call your attention to the fact that this is a very bad metal because the resistivity goes up above the Mott-Regel limit. So this is very non-classical transport behavior. As I said in usual classical transport behavior, you can never exceed the Mott of irregular limit. So this is usually called a bad metal, or perhaps in this case, a non-Fermi liquid. Okay, so that's the main lesson here, the main lesson to be taken home. The domain wall matter is a bad metal or a non-Fermi liquid. You can do a little bit better than that and do the following. If you look at the local density of states in the three solutions, the insulator has a gap, the metal has finite density of states, but you see that the unstable solution also has a very tiny quasi-particle peak at the Fermi level, okay? So it looks like a metal. If you just saw this, this is like Ricardo's talk yesterday. A very small quasi-particle peak for the insulating behavior. So if you just look at this, you say, well, this is just like a metal. So maybe you can do a metallic description of this. And a metallic description is usually done with a Fermi liquid Green's function. In this case, simplified because you only have frequency dependence. And in the Fermi liquid, the electron Green's function, in this case, the Green's function is described by perhaps two parameters, the Z, the quasi-particle weight, which basically measures the spectral weight of that central peak. So this should be small, one would think. And the imaginary part of the self-energy, which gives you the scattering, the inelastic scattering rate in the system. And if you follow those two quantities, the Z and the scattering rate, for the metal, you have what you expect. The Z tends to a constant. That's Fermi liquid. And and the scattering rate, the black curve here, follows T-squared law, right? This is what we expect in a Fermi liquid. But if you look now at this unstable solution, the Z is not only very small, but it's varying with temperature. It's going down, okay? So this is not what you expect in a Fermi liquid. And the scattering rate is shooting up, okay? So you have Z actually going like a T-squared law, and the scattering rate is diverging as 1 over T squared. Okay, so this is a although the description is based on a Fermi liquid-like Green's function, the temperature dependence of the parameter is not at all what you expect in a Fermi liquid. Okay, so this kind of description that relies on temperature-dependent Fermi liquid parameters has been done before in other contexts, the cuprates contexts, and it was called a non-Fermi liquid with resilient quasi-particles. So in a sense, there is some resemblance of a quasi-particle there because you have this Fermi liquid type of description, but the Fermi liquid parameters have very weird temperature dependence. In this case, it's extremely strong temperature dependence, as you can see here. So I come to the end of my talk. I hope I was able to convince you that although perhaps the metal and the insulators in a Mott transition are more or less well understood at this point, the domain walls between them, which we saw in the experiments, is very weird. And it's a very strange phase of matter. As I said, it has bad metallic or non-Fermi liquid behavior. And of course, in the future, what we want to do, you remember that I calculated the conductivity in the metal at the center of the domain wall in the insulator. But in the real sample, you have everybody contributing to the transport. And you want to know how everything conjures up together to get the final resistivity and conductivity that you measure. And this is something to be done in the future. And that's it. Thank you.
Well, thank you, Eduardo, for this very nice talk. So, questions here. We'll get here, and then Marcello.
Thank you. Thank you, Eduardo. Very, very interesting. Can we go back to one of the first plots you had? I think, was it the local density of states that went up, and then next to the the order parameter or the fluctuation length you had, one of the first figures you had?
I think I know.
Because I want to know how that reconciles with the fact that at zero temperature, at the domain wall, you seem to have an insulating behavior because it's because the quasi-particle peak goes to zero, the z goes to zero. Okay.
Yeah. So as I said, it's weird behavior.
No,
I think it's. I know what you're talking about. I think it's this one.
What is this? So this is the density of state at zero.
Yeah, but calculate. This is the Lagrange function at the first Matsubara frequency. Okay. So this is not. There no analytical continuation was done in this plot. Okay. So you can see sort of insulating-like, you can see metallic-like behavior, but you have to do analytic continuation if you want to see true frequency-dependent and temperature-dependent behavior. So this is, I would say, is a rough first shot at the domain wall. Okay, it captures a lot of the physics, in particular the domain wall size, because this is thermodynamics. But if you want to look at transport, which we sort of did here, but this is like a first shot. This is a very rough look at transport by looking at but not doing the analytical continuation to the real frequency axis. This is just the first Matsubara frequency of the local Green's function.
Okay, but I think it would still be interesting to see what happens at zero temperature, because I mean, from this, I mean, it's quite critical, and there's sort of a very critical treatment of the data you have to do, because from the first figures, it seems to be metallic, but then when you look at from the density of states, but when you look at the z, it goes to zero.
Right.
This is a little bit puzzling, and this is why I was.
I understand.
But I understand what you say, that this is at the first Matsubara frequency.
No, that was with that plot. Now here we did the analytical continuation. The best we could, right? Oh, sorry.
And there you get an insulator.
Let me see. Yep. No, let me say a little bit more about this. You can look at this, and even you can look at this, and I could end my talk here. Okay? This is conductivity behavior. So if you imagine that you have large domain walls and you somehow measure, you have two-point contact and you measure just the conductivity across, inside the domain wall, this is what you should expect. Now, this here is an attempt at parametrizing this behavior through a Fermi liquid-like Green's function. You may believe this or you may not believe this, but if you try to do this, what you get is that the Fermi liquid parameters do not behave as you would expect. That's all I'm saying. You might want to ignore this plot and look just at the conductivity data.
Thank you.
Okay. Just a final quick one. The only reason to do this is because we do see a quasi-particle peak there. So you are tempted to do this.
Thanks, Eduardo, for the talk.
Sure.
Probably it's a problem of terminology, but usually I'm used to listen about domain walls. Domain walls connect two states with the states are connected by symmetry, the two states of the domain wall.
Here, there's no symmetry. No.
It looks more like what people call a bubble.
Sure.
Your situation.
We also
not a
call
domain
it
wall, but a bubble, which is characteristic of first-order first transition.
That's precisely what we have here.
Okay.
We don't have a symmetry-relating method to the insulator. It's just the universality class of the transition is the same as the Ising model, which does have a symmetry between the two phases. Okay. But that's all we can say.
This would be not a domain wall, but a bubble.
Well, you have the bubble of the two phases, but between them you have a domain wall.
Yeah, that's what is normally called the wall of the bubble, but not the domain wall. But anyway, it's a terminology question.
Sure.
And it's more characteristic of a first-order first transition.
Yeah, you can actually, there is a way of sort of symmetrize the description. If you look along the line, and even above, there's a so-called Widom line, where the Landau functional is symmetric. But this is, you have to find the path in UT phase diagram that gives you the symmetric transition. But this is sort of very artificial. Okay. Yeah, Marcelo.
Okay, so I really enjoyed this talk. It's fascinating to see how so many years still DMFT brings out wonderful things. No, it's not a very specific question. It's just like, first, I don't think that you should call it domain wall. I think this is more general. It seems to be like you have in your system, everything is dominated. It's not a wall. It's just like a new phase. And then pushing that, speculating. Can it be way more general and even think of the cuprates that have in between the Mott insulator and the metallic state, which are at the ends of doping, and doping introduced disorder. You have the strange metal that people have been banging their heads. So do you think that this could be like
Yes.
more general?
Sure.
Yeah. So, yeah.
You raise the ball and I kick it.
Yeah, so for instance, what signatures should be in the magnetism of this,
Yeah, it's a good question.
mixed matter kind
We
of
didn't
thing?
do that. This is strictly finite temperature. We're not looking at low temperature instability, but that's a good question. You're going to have domains of the phases that are there, antiferromagnetism, superconductivity, perhaps.
But you could, for instance, with this stat DMFT, get predictions for the NMR and...
With magnetism, perhaps.
Yes.
Yeah, you could do it. Sure,
Yeah.
sure, you could do it. But you saw this is expensive calculation. A poor student.
No, there's lots of cheap computers. Come on.
No, come on, we were good.
Yeah, no, I enjoy it a lot.
Luis.
So yeah, I have a related question to the strange metal, because here, the strange metal, if I'm not mistaken, the resistivity is linear in temperature. And here, your resistivity seems to be decaying with temperature a little bit in the domain wall.
No, it's going up, right? At the domain wall, it's going up.
It's going up, oh.
Is it this? Yeah, it's this.
Yeah,
Yeah, sure.
So resistivity...
It's going up.
Okay.
Now, if you have a sample, you have everything mixed together in a continuous fashion, what does the resistivity do? I don't know. That's what we should do.
The question is this non-Fermi liquid behavior, can you map it to the strange metal for non-Fermi liquid behavior that you see in the cuprates?
So these papers, the papers that I quoted afterwards that introduced this concept of resilient quasi-particles, they try to push this description up above the Fermi liquid and towards the bad metal. But that's in the other context of cuprates, okay? But yeah.
Okay, I have another observation. You made a construction mixing a linear combination of the metal and the insulator, right? For the Green's function.
Yes.
So what I want to mention is that is exactly the same thing that we did with Andres to analyze his photoemission data across the transition. Yes. And it works very well. So I think that's a point that you should emphasize. There is experimental evidence for that construction that makes sense.
Yeah. I'm just saying that the actual final Green's function is not of this simpler form. It's a little bit better because we use this as a first guess. And then using Breuden, we go towards the unstable solution. It's not exactly of this form, but probably very close. So
okay, but one thing, just to connect to the, as Andres emphasized, ARPES just gives you a snapshot, a photo of what's going on. And one thing that I think is not resolved is whether you have, and we discussed this with Andres a lot, whether you have a new state, which is rather homogeneous during the transition, or you really have to think of patches of metal and insulator?
I think based on the scanning microscopy I showed, You have to think of patches. Because I don't know, maybe you should be able to answer this. I think ARPES does sort of an average, right?
Yeah.
So
It can be both.
But if you have a local probe, you do see the patches. That was my point. It's there, right? Or here. Right? It's real life.
Yeah.
Now, you might say, well, this is not disordered. But you know that VO2 has this elastic coupling to the... VO2 is complicated, right? But I think here it's cleaner. This is V203. And you have the patches there. I think what you're saying to me is that if you have a probe that doesn't have resolution to see the patches, you sort of average out everything, and I agree with you. But if you have a local probe, like NMR or this, you should be able to distinguish the two things.
Yeah.
No?
I don't know. What I'm saying is that those patches are still like a picture with a lot of, you know, I want to call it massaging, but there is like not totally identified scales.
Well, here I think it's pretty...
And the electronic properties, maybe, yeah, still, I mean, I know these things. And there are many questions.
Look,
that one can...
Look, Vlad did this dielectric constant calculation, which is basically what you said.
Yeah.
He did sort of an average, and it fits beautiful with the data by Martin Dressel, dielectric constant measurements. It's just an average. So I think it depends on the probe, the resolution, and everything. Probably most probes, an average will be enough.
Yeah, but
not always.
The only point that I'm making is when you have metal and insulator, and the metal does not percolate, then everything may be dominated by the in-between matter.
Sure, I totally agree. That's my point. That's my gospel.
Let's get here, Lenny.
Hi, thanks for this very beautiful talk. One question, let me be sure if I have understood. So when you are looking at, you are getting this non-Fermi liquid behavior. What you are doing is you are looking at the first Mott, so at the sigma at the first Matsubara frequency, right?
Just at the first calculations. Then we did the full analytical continuation. The second part, the last part, we did the complete job of analytically continuing to real frequencies.
Okay, and then, so my question is, in Matsubara, the shape of sigma as a function of Matsubara frequency. So what you are getting, it's going linearly to zero as much as it can. It is not going linearly to zero as much. Because I say also as a way to define.
So if you just look at the Matsubara frequency.
The quasi-particle weights and all that. So.
No, so to do that, you have to do the analytical continuation. The Matsubara is not enough. Okay, and that's what we did. That's the main result at the end. But if you just look at Matsubara frequency, you can have rough behavior that's compatible with metal. So, for instance, in the metallic case, the self-energy goes to 0, and in the insulator, it diverges, right? Or you can look at the Green's function. The Green's function in the metal goes to a constant. It goes to 0 in the insulator. And that's what you can see. It's very clear. One goes like this, the other goes like this, and you can distinguish them. But you cannot do more, okay? This is rough. But it's rough, but it's very qualitatively different. But if you want to look at the detail, conductivity and so on, you have to do the analytical continuation. That's what we did.
Okay, okay, then I think you're answering my question. You are not getting the quasi-particle weight from the first value of the Matsubara frequency,
not at all.
From the all, okay.
Thank you. Marcello, last one.
No, just I have a comment that in COOP rates, in fact, the resistivity go up when they apply magnetic field and they recover the SO that is compatible. However, before jumping and said that this can work for the COOP rates, you should perhaps stop and see what happens with the pseudo gap, because there are features on the pseudo gap in the metal of COOP rates which are very well established, and it's not clear that in this scenario this can be explained. I have a last very quick question. if you simplify the problem enormously, and you take an interface between a Mott insulator and the metallic one, will that interface get the same kind of physics?
Yes, that's what was done here. We did a one-dimensional calculation. Yeah, we did that.
So thank you. We had a lot of discussion, but let's thank the speaker again.
Sure, thank you.
The next talk is William Nattori.